Hi everyone. Today I'm going to talk about a system that I built to basically measure height above the ground for an aircraft that is coming into land. Typically, this is usually implemented using radar altimeters in more expensive aircraft where they have a separate instrument that shoots a beam of radiation light or some radio waves into the ground, and the reflected wave comes back, and the time is measured, and then using that information as the speed of light, it can calculate the height above the ground. So this is an exact height above the ground, down to probably in the order of inches or fractions of a foot, that is used for landing aircraft with high accuracy under conditions that may not be very good for visual conditions especially. So main thing we need to talk about here is the different types of altitudes that can aircraft we talk about in terms of whether it's above the ground or whether it's above mean sea level. So that it tells you the height above a certain plane. That's in many cases the Earth is, as you know, is not a spherical object. So it basically has an ellipsoid kind of a shape, which means that the absolute altitude above the ground cannot be calculated based on a certain geometrical thing. Um, Although when we have a MSL altitude, we determine that using barometric measurements typically, or using GPS, where it's corrected based on wide area augmentation system called WAS, which allows you to locally correct for imperfections in the datum, that is the plane that is used to calculate what is considered to be ground level, which is 0 foot. But in this case, we can't depend on any of those using barometric or GPS, because there are corrections that have been made and they are not accurate enough to be landing in very, very poor conditions where the visibility is down to very, very short distances in the order of hundreds of feet or less in terms of altitude. Anyway, to cut a long story short on this whole thing, what we have is MSL, which is accuracy, which depends on the altimeter setting, and that we convert to an AGL if you want to know exactly the height above the ground. But in this particular case, when we use LIDAR or some kind of an electronic light-based system, we can actually shoot some radiation down to the ground and measure the distance that way, using the time of flight as well as the speed of light. So that's the most accurate way of doing it. For our aircraft, the typical GA, general aviation aircraft, these instruments are very expensive, and the certification, of course, is not is a difficult process for most of these certified aircraft. So there are ways you can get around it by using these type of systems, which are not certified, but at least they are an aid to landing. They are not meant to be a primary source of information as far as like a altimeter or something like a radar altimeter, which may be certified. So let's talk about how this works. In particular implementation, what I have is this thing which I call LandSafe, a LIDAR based landing height system, which is operational at about 50 feet or a little bit higher depending on the surface reflectivity of the light that is being emitted by the transmit sensor. The receiver then picks up that light, and the time of flight basically allows me to calculate the height above the ground. So because of the reflectivity changes, the altitude at which this thing can work also will change. If it's very, very poorly reflecting, the height above which it can measure will actually decrease as well. So you want a good reflectivity, like 90%, like a really good shiny surface. You'll get a much higher range in terms of the sensor and the receiver being operating. So what this will do is actually under 50 feet is where one is really interested when you're landing. You want to, as long as you're not coming down too quickly, 50 feet gives you enough time to basically measure your descent rate and control your landing flare and so on, to be able to land smoothly. So this particular instrument will announce at 50, 40, 30, 20, 10, and then at intervals of 5, 4, 3 to 1 foot levels, and it will voice enunciate that, and so it will give you a visual, audible as well as visual indication of where you are when you're descending. So that's, since you're looking outside, you're not actually looking at this instrument. You want to be able to hear where you are. Although occasionally you can glance at the instrument to see what the height is, the actual height is in feet and inches. And then in case of a climb out, let's say you do a go around, that means you think the visual conditions are not good, or your sight picture is not good enough that you feel that you're not comfortable landing, you could go around, and this instrument will then start essentially increasing the height level that it's actually seeing, and it'll at some point where it loses contact with the ground, that it'll basically peg at that last held altitude that it found. It could be 40 feet, 50 feet, whatever. And in the examples I will show landing up an aircraft, and that altitude will change where it starts to work and where it stops working. So there are things you have to worry about. But in general, below 50 feet or so, it will start typically engaging, and the information that this instrument will start displaying will be valid at some point. So that's the good thing about it. It will actually reset itself on landing. And then on the instrument display itself, once I show you, you'll see that it has got a tape on the right side, which is like a indication of the height with a mark with a horizontal line across it, which shows you the actual height. It also displays the height digitally in feet and inches. And there's also an LED, 3 LEDs actually. One is the blue LED, and the second is the yellow, and the third the red. So the blue is operating anywhere between, when the plane is between 25 and 50 feet, the blue LED will light up. When you go between 10 and 25 feet, the yellow comes in, and then below 5 feet, when you're just about to land, the red LED comes on, and then when it's at 0, actually it'll announce your touchdown, or basically you're at 0 feet, essentially, that your touchdown. So these are the way this instrument will communicate with the pilot, and hopefully this is not, you don't have to be looking at it, luckily. So that's one good thing. You're looking out at the runway, the side picture outside to make sure you're landing. But this gives you an additional information, especially if your conditions are not that good, you're not familiar with the airport, the runway looks, sometimes there are visual distortions, especially with certain types of runways which are long or extra narrow, extra wide. So they have different side pictures which confuses the pilots, and that they tend to flare early or they flare late. So you want to avoid those kind of things which can damage the aircraft on landing. So this particular indicator or a landing height system will actually help you to realize that what your real height is above the ground. So here's the hardware setup. It basically consists of this ESP32, and it's called the TS0636 GT display. And it's got a fairly long name with a bunch of features, including Bluetooth, Wi-Fi, and a 1.14 inch display. Initially I was using as I mentioned, I don't know if I mentioned this, but the Arduino Nano to develop a simpler version of this one, but the Nano is really not powerful enough to handle such a more complicated functions, as well as the speed at which it needs to operate. Clock frequency is quite high on this one, and so it can actually do a lot of computation and parallel processing in terms of the IOs and so on. So this ESP32 is programmed through this USB-C port. It also provides the power for the rest of the peripherals out here. So the main thing is the sensor, which is the TOF Future, they call it TOF Future XTS1 sensor. It's a 0.3 meters to 30 meters distance. 30 meters under good conditions, 90% reflectivity. I would say it's about 8 to 10 meters with 20% or lower reflectivity. So it's not going to be very effective at very dark surfaces or rough surfaces, I guess. So one has to account for that. So my calculation was more or less 50 feet and below it would be okay. And there's the DF player mini, which does the voice part of it. You need to have an SD card which has all the voice commands, like you want to say 50 feet, 40 feet, whatever you want to give information. It has to be properly recorded in MP3 format and put into this SD card, and then used to basically trigger the correct annunciation given whatever this computation is going on as far as the height is concerned. And then there is the 3 LEDs over here, which are driven by 3 ports, which just general purpose IO ports. I think I used 25, 32 and 30 on this one. I should probably write that down. And the other ports over here are which are used for the UART communications. There's a 26, 27 for the transmit receive for the sensor, and on this also using a UART is using 21 and 22 on the ESP32. And if you look at the specs or the data sheet for this player, it's got 8, actually it's got I think 14 pins, but I think I only use about 6 of them. So the 2 of them are used for the speaker, and then the 4 are for the communication and the power. Same here. This actually one of the inputs to this one, the RX input is actually 3.3. So they suggest using a voltage divider, or you can get away with a series resistor, I believe also, which is what I did in this particular version. It seems to work fine. Doesn't have any issues with that. And for this one, you need to make sure you have a good 5-volt input at least. Typically, the USB-C that provides the 5-volt, actually, when it shows up on the 5-volt pin on the ESP32, is actually at 4.2 or something. So you might want to just directly access the 5-volt coming out of the USB over here into this port. That's why I showed it separately as an input. You could essentially also connect an external 5-volt supply if you have one to drive this, because this is the main part that requires a certain amount of good deal of power, at least 100 milliamps I believe, to make it work. Any power voltage reduction would also degrade the range, I'm guessing. So this is a setup for the hardware. It took a while for me to get this to work on the software side, and also it spent a lot of time actually developing that software. I used AI to basically do the software part of it, because I'm really not that good in writing software, and especially this was fairly complicated. I did not know the coding, the language exactly for this one, and a lot of UART communications which I wasn't that familiar with, so I let AI do the job. I spent a lot of time back and forth on debugging the software. I think right now it's working. It's fairly long. I'm not sure, because I guess it's a little bit inefficient the way it developed it over a period of several weeks. So it could be, I'm sure, much more efficient, shortened, and but right now it's over 800 or 900 lines of code, I guess. It's probably overkill, but I think it works, and this particular hardware is good enough to handle that, along with the display. I'm not using the Wi-Fi or the Bluetooth, although that could be used if you want to basically communicate the same thing through a headset on an aircraft. You could have Bluetooth communications, and you don't have to have a speaker and so on. But I think the speaker is a nice touch. I think other people on the plane can actually hear it when it's being announced, so it's actually nice that way. You could also drive this into I guess into a jack or something, a headphone jack, if you wanted to do that. So I think from an initial development point of view, I think this is a good setup for just the hardware portion of it, although it could be improved and expanded. The following 4 slides will go into some details about the hardware, starting with the Tow Future XTS1 sensor, which is the main part of this instrument, which is the transmit receive LIDAR device. It will operate at 940 nanometer, as I mentioned, and I'm not going to go into the details reading out all the specs. You can stop the video at any point to see the details, to also find out the model numbers and part numbers and so on. So I'm just going to leave it at that. I'll also talk about the ESP32 device and the DF Player Mini, which is the audio device which plays back MP3 files. A few words about the software. This was developed on an Arduino IDE platform using mostly AI help. I'm not, as I mentioned before, a great programmer, and especially with this new device, I had very little information or knowledge about it, so I pretty much depended on AI to do this. So the features, as far as I've implemented so far, it's a landing height system which works from approximately 50 feet down to 0 feet in 10-foot increments at the beginning, and then 1-foot increments below below I think 5 feet, yeah. And it's got a maximum height of about 150 feet based on the sensor itself, but that's assuming 90% reflectivity, but with typical reflectivity of 20-30%, it's down to about 50 feet or so. It displays a tape and indicates the height on that tape up to 100 feet, like with a horizontal line. It's got a 3 LED display for visual impact and to basically garner attention. It uses a moving average filter to smooth out sensor noise. Has an error counting function which displays if there are any bad height readings. Of course, that's not currently displayed. I've taken it out for now. Has also implements a go around detection and arms the thresholds dynamically while climbing or descending if there's a level off or something like that. So it will actually adjust the thresholds at that time. It's got voice call out cooldown function which will prevent it from reading out too many call outs at the same time. Like if it's transitioning from 5 feet down to 4 feet to 3 feet, it'll probably skip a few in case it's happening too rapidly, so that prevents confusion or incoherent response. Several improvements are being made. One is to make sure that the 0-foot touchdown is consistently called out. The logging feature can be added to evaluate landing performance, so you can probably find out whether you landed smoothly, whether you flared or you kind of bounced and things like that. Voice muting and diagnostic functions can be added, and finally rate of descent indication and excessive sink rate warnings could also be added. So I think that's enough for the software, and now let's look at some flight results. So here's the constructed unit. It's 3D printed on a Creality printer. It's a fairly small device, about 110 millimeters by 60 millimeters, which is the X and Y dimension, and it's about 25 millimeters deep. And it fits, all the parts fits within it. On the left side you can see the speaker, which is about 50 millimeter type size speaker, and the display is to the right with the 3 LEDs on top. The power supply comes in on the right side, the USB, and on the left side you can see the 4 wires going to a connector, which then goes down, routed down temporarily to the outside of the aircraft through one of the air vents, and the sensors mounted under the wing. So I calibrated out the wing height, which was about half a meter or so, and took that out of the equation as far as the height of the aircraft above the ground. So that gives you a 0 level. So here's the flight testing portion of it. I'm going to demonstrate this instrument using a Mooney aircraft. It's installed on the top of the dash, and I have somebody photographing the actual instrument display Unfortunately, because the conditions were very windy and gusty, the actual video was actually quite jerky, and did some stabilization in the video software, but because of the stabilization actually reduced the field of view, trying to keep this information steady. So you might find that the actual display might go out of the screen itself. So it'll it hopefully is visible enough that you can see the numbers and so on, and the tape and other features of this thing. So the first thing is a go around where I descend the plane all the way down to about 3 feet above the ground on the landing, but don't actually touch the ground. So you'll see the value go down to around 3 feet or something, and then I do a go around and then come back to do a full landing, and then the third landing will be a full stop. So let's start with the first one. So this brings us to the end of this video. Hope it was enjoyable. I learned a few things, especially in system level side, software, and putting together the whole thing in terms of the hardware and software, sensor and everything else. It's, as far as electronics itself is concerned, is really not much in here. It's just a question of understanding the limitations of the hardware, as well as getting through the software portion of it through many prompts and debugging the software to make sure you got what you wanted. So that's it for now, and hopefully I can make a few more improvements, and I'd like to then install this properly in the aircraft. Thank you.